Okay, so continuing with the trig identities, we ended up doing some angle sum and difference formulas and double angle formulas, which kind of allow us to do some new things. So in the current pre-calc book, this was sections 5.3 and 5.4. So if we take a look at some of these you really just kind of need to sit down with them for a few minutes and just kind of get them down in your own way. But they say something like this. There's a couple patterns here. You can either do the sine, the cosine, or the tangent. Um, and they can be a plus b or a minus b, so I'll kind of show both in those. But with the sine of a plus b, the little trick to remember is you're going to use the opposite functions, so sine of a, cosine b, so one of each basically, and then use the same sign, meaning a plus or minus, and then the functions just switch spots. So cosine of the first, sine of the second. There should be a b there. Um, and if the original problem happens to be a minus in there, you have a minus in the formula. So we write it this way just to save time so we don't have to write the formula twice. That's kind of like two formulas in one. Okay, for cosine of the sum of two angles, it's going to be a little different. It's cosine of the first, cosine of the second, and then it's the opposite sign. Sine of the first, sine of the second. So the functions are the same, like it's cosine goes with cosine and sine goes with sine, but the symbol, the addition or subtraction, is the opposite. And likewise, if this one's a minus, in the formula it would be a plus on the other side there. Okay? And then tangent, um, the numerator is actually just like if you were able to distribute the tangent from the left side of the equation. Okay, so it's kind of just like distributing tangent of A plus tangent of B, and the denominator is always one opposite sign tangent A times tangent B. And then similarly, if your original problem, if you were subtracting two angles, the numerator would have the same sign while the denominator would have the opposite sign, so it would be a plus there. Okay, so using those, that will help us do some things like finding the sine or cosine or tangent of some angles that are not on the unit circle. Okay, so for an example, if we wanted to find the sine of 195 or something like that. Okay, so we don't know that value. Okay, but you should know exact values for everything on the unit circle. So of course you could just throw sine 195 in a calculator and get some decimal out, and that's an approximate, but to be exact, we kind of got to do it this way. So what I would do is think about your unit circle, think of 30s, 45s, 60s, 90s, okay, or those as reference angles in any quadrant, and come up with a way to get 195. Okay, so I would kind of think of either doing 150 plus 45, that might be a good one, or you could do 135 plus 60. Um, and there's a bunch of different ways here, but basically I'm going to set it up. I'm going to do 135 plus 60. Okay, so that's going to be like your A and your B. And we should know each of those values exactly from the unit circle. Okay, so if you need to refresh on your unit circle, go ahead and do that. But the 135 you can think about as being in the second quadrant with a reference angle of 45. So that one, sine and cosine, are both root 2 over 2. It's just that the cosine happens to be negative there. And then with the 60 being in the first quadrant, we should know those from the unit circle. But let's plug in some values. So the sine, if we just go up to the way the format's written right up here, we know what our A and our B are now. So we're going to need the sine of 135 times the cosine of 60. And we're doing a plus, and then we switch them up. Cosine of 135 and the sine of 60. Okay, so that's how that one's going to get set up. Let's see if we can just make some more room down here. And then you just kind of go through and plug each one in. Okay, and kind of simplify. So the sine of 135, again, thinking of this angle up here, 135. The sine there, we're in quadrant 2. The y value up there is positive, and it's root 2 over 2. The cosine of 60 is going to be 1/2 from the unit circle. And then we switch them up. Cosine of 135, that's the one that's negative root 2 over 2. And the sine of 60 is the square root of 3 over 2. And then you just kind of need to do the little arithmetic here. We're going to multiply straight across here, so that's root 2 over 4 plus negative root 6 over 4. Okay, so I had some people leave it that way, which is fine. Or you can just kind of combine them into one fraction. They do have a common denominator of 4, and the numerator is root 2 plus negative root 6, which is really just root 2 minus root 6. Okay, and that would be an exact value for the sine of 195. Okay, if you need a cosine, it would be very similar. You can just follow the format for cosine a plus b. Um, I'll show you the tangents a little bit different just on the simplification. But let's do a tangent problem here. Why don't we do like the tangent of like negative 15 degrees? So let's, as an example, let's say we want the tangent of negative 15 degrees. Okay, so again, come up with a couple angles that work. So I'm thinking one's nice first quadrant angles, 30 and 45. And the order is going to be important here. It's 30 minus 45 to get a negative 15. Okay, so that's going to be my A and my B. And I'm using the minus rule here. So the numerator is just going to be almost like, again, if you imagine distributing that tangent. So tangent of 30 minus tangent of 45. And the denominator, 1, opposite sign, so plus the two tangents multiplied together. Okay, so that's going to be our setup, plugging into the equation up there. Now we just need to remember these values here. So the 30-degree angle is the shorter angle in the first quadrant, so it has the smaller tangent, so it's going to be the root 3 over 3. And the 45 is right in the middle, so it's going to have the tangent of 1. Okay, so let's plug everything in. Tangent of 30, we just said is root 3 over 3 minus 1 all over 1 plus tangent of 30 again, root 3 over 3 times 1. Okay, and then just to do a little simplification, um, there's kind of a few things we should do, but we really don't want to have fractions inside fractions. They're called complex fractions. So what I notice is both numerator and denominator have a fraction with a 3 in it. So we can multiply the top and bottom by 3. So we're really just times them by 1, right? 3 over 3 is 1. And all it's going to do is kind of clear out those denominators. So if we were to distribute the 3 to both of these, the first term would just become root 3, okay, because its denominator here would be canceled out, minus the 1 times 3 is 3. And then same thing on the bottom, just distribute the 3 there to get 3, and then 3 times that term, again, the 3 will just cancel out. Okay, and I'm okay with you leaving it like that. Technically, we don't like to have square roots in the denominator, you might remember, so we would multiply by the conjugate, multiply top and bottom by 3 minus root 3. But it's just kind of little small details, so I'm going to kind of let that go. Okay, so that would be, okay, and remember to check any of these, go ahead and do, you know, in your calculator, type this whole thing in carefully, of course, with parentheses and everything, and you're just going to get some decimal and make sure that it matches up with what the tangent of negative 15 is. And if those are the same, you know, we did things right. Okay, so one other thing with these angle sum and difference formulas is it allows you to do double angle. Like for instance, let's say you had the sine of 2x or the cosine of 2x. Okay, or even the tangent of 2x. And there's a little shortcut formula that will allow you to replace those in terms of just x. Okay, so if you have an equation to solve, everything will kind of be on the same page. And those come directly from the ones we just did, the angle sum and difference formulas. Okay, so if you take a look, I'm just going to use those exact ones. I'm going to use this. Okay, so when I want to do the sine of 2x, I'm just going to treat it as the sine of two angles added together. Okay, the cosine of 2x, I'm just going to use this kind of setup here. And the tangent actually comes directly from this one as well. Okay, so we'll kind of go through the details on one or two of them, and then you can just trust me and just kind of learn them, or just use these ones that I highlighted to get the new ones. Like you don't have to memorize them both. So what I mean by that is, let's just do like the sine of 2x. If you see that anywhere in a problem, you can think of it as the sine of x plus x. Okay, just note though, because I saw a couple people, this is not the same as the sine of x plus the sine of x. Okay, that's not the same. That would be 2 sine x. In our case, we have the 2 in with the angle there, so that's why that 2x lines up with the x plus x. You're taking the sine of a double angle size. Okay, so if we just treat this as our a and our b and use our rule for the angle sum and just expand it out, remember it's sine of the first times cosine. Oops, I want to use x, right? Both a and b are x, so sine of x, cosine of b, which is x, plus, and then we switch up the trig functions, cosine of the first x, sine of the second x. And since both a and b are both x, right, that allows certain things to occur here. These terms are actually the same thing. It's sine times cosine and cosine times sine. So it allows us to write it as 2 sine x cosine x. So that's technically your double angle formula for sine 2x. And it has just the one version. Okay, so if you see an equation, okay, like we will do in a second here, or we might as well do one now. If you see an equation with sine 2x in it, let's see how we would solve it. So for example, or even if it's in an identity, you can do this replacement, but let's say we had an equation to solve. Let's say the sine of 2x equals the cosine of x, and they want us to solve for x on the interval 0 to 2 pi. Okay, so this is not an identity. We're not proving, that these sides are equal to each other, because this is not an identity. Like, they're not always equal. Okay, there are some x's that make this statement true, but there are some that don't. So we're trying to solve and find out which ones make it work. Okay, so the trick is that 2x in there, we're not on the same page as the other side that just has an x. So what I would do is use the replacement. Okay, this whole thing right here, we have another way to write that. Okay, we just wrote it right above. That is really just 2 times the sine of x times the cosine of x. Okay, so now all the trig functions are related to just x. The only angles in there are x. So the next trick where you need to go from here is try and get one of the sides equal to 0 so we can try and factor this thing. So if we subtract that cosine x over, okay, minus cosine x equaling 0, and now we're going to have something that we can hopefully factor, or in some cases we'll see in a minute you might need to use the quadratic formula. Okay, but in this case, I see a common factor in each of these terms. They both have a cosine x. Okay, so I'm just going to throw a 1 there just so we can keep that in mind. So I'm going to bring that cosine x out front. Okay, it's common. Okay, if this cosine x is brought out front, the remaining term is this 2 sine x minus, and if again that cosine x is brought out, we're just left with a 1, and it still equals 0. Okay, and what that lets us do now is, since it's factored and it's equaling 0, I know the only way things multiply together to equal 0 is if one of the things is 0. So I can set the first factor equal to 0, and I can set this other factor equal to 0, and we can hopefully solve those for x and get some answers here. Okay, so this left piece here is basically asking what angle, okay, what x value has a cosine of 0. Okay, so if we think on our unit circle, cosine 0 is going to be when the x coordinate is 0, so right there and right there. So those two angles in radians are pi over 2 and 3 pi over 2, right? It's your 90 and your 270. Okay. And now the other one has a little bit of work we need to do, add the 1 over. Let's try and get the sine x by itself. So we'll add the 1, we'll divide both sides by 2. All right, and now we need to ask ourselves, what angles have a sine value of half? Okay, so again, knowing your unit circle. Okay, the sine of half is the lower angle. It's 30-degree angle right here, pi over 6. Okay, 30 degrees. Or there's another positive signs in the second quadrant. If that's 30 degrees, that would make this whole angle 150, okay, which in radians is 5 pi over 6. And there's your answers. Okay, so that's an equation involving sine of 2x that is useful. Okay. For the other double angle formulas, let's just do we did sine of 2x equals, this was the one we just did, right? If you have cosine of 2x, okay, it's a little bit different. And the reason is, again, if you go back to the sum formulas, x plus x, okay, so your a and your b are both x. The way the cosine one worked, if you remember, it's cosine of the first. Oops, I keep wanting to put a, but a is x. Cosine of the first times cosine of the second minus sine of the first, sine of the second. So this one algebraically is just a little bit different. It's actually cosine squared x minus sine squared x. Okay, so that's your main double angle formula for cosine. Okay, and what you may find in some of the equations is that maybe it has only cosines in it or only sines. So you are able to replace, if you need to, you can replace that with 1 minus sine squared to get a different variation of this formula, or you could similarly replace that with 1 minus cosine squared x if needed. Okay, so look at the problem, see what you got to do. So there are 3 versions you'll see in the book. When you do cosine of 2x, there are 3 versions, and it just depends on what you want in there. Okay, and then finally the tangent one, just to finish everything up. The tangent one, I'll show you that one real quick. Okay, that one again, same thought process, x plus x. The tangent rule is always tangent of the first plus tangent of the second over 1 minus those tangents multiplied together. Okay, again, this is when a and b are both the same. And you just algebraically, numerator is 2 tangent x. Denominator is 1 minus tangent squared x. And that's your double angle for tangent. So again, I encourage you, don't memorize these if you don't want to, but you have to know the sum difference ones from the previous pages, highlighted ones here. They'll get you a lot of other answers. All right, hopefully that helps with your tangent, cosine and sine, double angles, and sum and difference formulas.